project, the same as the conversion of food waste into the packaging material. The first step is we are converting biomass into the nanoparticles and then into a packaging material. There is the introduction, like there are most in the world is the food waste or the waste of food. There are approximately 1.3 billion tons of the food waste in the world annually. So by these there are a lot of greenhouse emission and there is an environmental pollution also. So for reducing this pollution and greenhouse gases, we are just converting them into the useful material as packaging. So by using the same nanotechnology as a solution, we are preparing the food waste into the packaging. Here I have taken food waste of orange, sweet potato and banana peels, as these are rich in cellulose, lignin and starch. As this is more suitable for the making nanoparticle synthesis, and by choosing this waste, we can also reduce the waste and also the material cost. We don't have to cost anything for the material. So this is the thing, and the same thing as Pascal did. I am just showing it in the flow diagram. These are the waste we have collected. One is banana, orange and the sweet potato peels, and then we dried it for a week in an air dry in the laboratory, and then we grind it into a powder, and then we gone through a pyrolysis. Here we used micro furnace. This is the micro furnace which is used in the engineering lab for making the biochar. With the thing we used 550 degrees Celsius for 15 minutes to go through this process. Here is one of my sample of the biochar. I have three samples to be done, but there is only one sample done with the biochar right now. And then I have autoclaved it for 4 hours, 160 degrees Celsius. This is the biochar. I have added 50 ml of deionized water and to this, and first I have sonicated it for the 30 minutes, and then I have autoclaved it for 4 hours in 160 degrees Celsius. And after collecting these from the autoclave, we have did it for the centrifugation. It's gone like the RPM of this was 600 RPM for 1 hour. Actually, it should be like 1000 RPM for 30 minutes. So we don't have that much RPM here. So we are using the 600 RPM for 1 hour to get centrifuge and suspended particles on
That
them.
should be 1000. I mean, that machine can go up to 4,000.
6,500.
So you're mixing it up.
We use
thousands.
6,500.
Sorry, we should use 10,000. We are
10,000,
using
yeah.
6,000.
Yeah.
Here is the thing, we have converted waste biomass into nanoparticles. And here is the film preparation. Here we are using ketosane and polyvinyl alcohol. And PV, we also call as PVA.
PVA.
Pascal has explained about what PVA has done and how we prepared films with the PVA, and also we prepared films with the ketosane. Here, as we have taken 2 grams of ketosane and 49 ml of deionized water and 1 ml of acetic acid. We have first mixed mix this deionized water and acetic acid as a solution, and then we have mixed it in the 2 grams of ketosane. After this, we have kept it for the sonication for 20 minutes for getting it mixed. And then after that, we have added 30% of glycerol, that is 480 ml. That is 30% of polymer. Glycerol is added based on the polymer. So we added 480 ml of glycerol to the solution. And again, it is sonicated it for 10 minutes for the mixing of all the solution. And then again, we heated it on a stirrer for 100 rpm at 60 degrees Celsius for 2 hours.
Okay.
Then again we have prepared films with the solution which we have prepared. This is the future work we are going to do. We have prepared the solutions right now with the ketosane and PVA. But the next we should go with the we should add nanoparticles to the solutions, and then we should prepare films, and then also the characterization of all the samples.
Great. All right. Thank you. Good afternoon. Any questions? Yeah, please. Sorry.
Well done. I didn't know you were working with ketosane.
Okay.
Sonicating ketosane can sometimes break the polymer into shorter chains. But if it works for the film, then it's still fine. But it cuts the polymer into shorter chains and then will be more. Because I'm the one I advised her to sonicate it.
No, in the protocol they use, the materials they use, it's desonicated there.
Yeah, anyway, I guess if you sonicate it for a short period.
For
it's
30
fine.
minutes.
That's a lot. Yeah.
No.
It's because it breaks down in into shorter polymers. It will still be a polymer, but it just becomes a short chain.
Yeah.
Did we even sonicate? No, we didn't sonicate that after adding ketosane. No, we didn't
You didn't
Yeah,
sonicate.
sonicated it.
You
Oh,
did.
really? Okay.
Yeah.
You
But
did.
it's not colliding.
Okay.
It was
It's
so
not
much
getting
loss.
mixed,
So okay.
Okay.
so that we have sonicated it.
So the sonication is for what? To get
To
it to
mix
mix.
it.
Oh, yeah. What about using vortex and or steering
It took too much time, so
to stir?
No, it's not getting too much time, but it's not getting mixed. It's like forming
Mixed with
lumps.
what?
With the deionized
Water.
With
we
water.
are making solution for that
Deionized
with
water.
deionized water and glycerol. So, but it's
Okay.
not getting.
But okay, let me understand this. How does PVA come in? Are you mixing PVA, the ketosane, and no, just separate?
Separately.
Yeah, I think you shouldn't bother yourself so much about the PVA. PVA is soluble in water, forms very smooth pastes. I don't think you should bother yourself so much with it. And the ketosane is not going to be transparent anyway. It's not going to form. I think focus more on PVA. Try first thing, do PVA. If you have time, you can worry about it. If you don't worry about it. Don't worry yourself. Or you want to try it. I mean, I'm happy for you to try anything you want to try, but in the interest of time, or what do you think? Yeah,
We can try because it's still the same time. It's just mixing and then it's still the same
it's still
period.
the same.
Yeah.
Okay, all right, yeah. If you want to try, I'm happy for you to try, but I'm more concerned on focusing on one thing, getting it done, and writing up your report. Right.
Just copy.
All right. So general advice. You see the way she's presented this scheme is really good. She use it for a poster. You understand? It doesn't take space, and it's easy for anyone to understand. You understand that? You see, you say, oh well, we dry it, we grind it, we pyrolyze it. I think it's much more it's
Schematic.
yeah, it's more schematic and it's easy to flow. Especially for your poster, you're going to make posters. So just try to do something like this on the poster as your methods. You know, under your methodology. Apart from you have not talked how you make the thin film, so you need to add that one. You understand? Okay. You need to add your thin film. Yeah. Okay. What else?
I'm just like curious, are they going to assess the mechanical properties of the film, like to see different concentration of this road?
Yes, that's
That would be,
yes, that's the plan. But I don't think they'll have time to do it. Yeah, but normally we're supposed to do some dynamic mechanical analysis where we test the strength, all those sort of things. But we're going to do SEM. First, we need to make sure that the films that are made are okay. What's the distribution of the particles? So SEM and TGA, all this XRD, we'll try to do. But I'm happy for you to stop wherever is comfortable for you. Yeah, and I think you still have some time anyway. You have the whole of April to finish off everything. But again, you need to be writing alongside. Yeah. All right. Thank you, Mona. All right. Oh, sorry, Bhavani.
It's okay.
I'm done. I'm done. Not yet. Not yet.
Okay, so after you, then we're going to listen to Biosensors presentation. Okay, so yeah.